You know, the equations that describe a simple stream of water, what if they also hide a secret that could just shatter our whole idea of cause and effect? Today, we're diving deep into the Navier-Stokes equations. These are the formulas that govern how fluids flow, everything from a tiny droplet to the swirling heart of a hurricane. But hidden inside them is a mystery that has stumped mathematicians for almost a century, and it comes with a $1 million prize. So here's our game plan. First, we'll unpack why this fluid problem is such a big deal. $1 million big. Then we're going to meet the two types of solutions that have been at the center of this battle for decades. We'll get to the heart of the uniqueness paradox, see how a digital breakthrough changed the entire game, and finally, ask the big question. Does this math point to a world with infinite physical realities? All right, so what is it that makes a set of equations so incredibly hard to solve? Well, it all starts with just how much they cover. They are trying to describe nearly every single fluid we see around us. For the better part of 200 years, the Navier-Stokes equations have been the absolute best tool we have for modeling all this stuff. You can think of them as basically Newton's second law, F equals ma, but beautifully and complicatedly adapted for fluids. But here's the catch. We don't actually know if these equations always give us a single, well-behaved answer in 3 dimensions. We just don't. Proving that they do, or finding a case where they break down, is so fundamentally important that it's one of the 7 Millennium Prize Problems. And yeah, there's a cool $1 million reward waiting for whoever cracks it. The whole massive problem, it really just boils down to a fight, a fundamental conflict right inside the equations themselves. On one side, you have the villain, this nonlinear term. This is the part that lets a fluid's own motion feed back on itself, creating the beautiful and chaotic mess we call turbulence. And on the other side, you have the hero, the viscous term. This is like friction, always working to smooth things out and dissipate energy. The $1 million question is simple. Does the hero always win? So this epic battle, raging inside the equations, it forced mathematicians to get really, really creative. And that led to a brilliant, but as it turns out, a deeply problematic new idea. For decades, that villain, that nonlinear term, was just too powerful. Progress totally stalled until 1934. That's when a French mathematician named Jean Leray had this incredible idea. He basically said, look, what if you can't find a perfect point-by-point answer? Well, what if you just redefine what an answer even is? He suggested we could accept an average solution instead of a perfect one. And just like that, the concept of weak solutions was born. Okay, so first up, you have what's called a strong solution. This is the one we want. It's the gold standard, it's perfectly smooth, totally predictable, and if you start with one set of conditions, you get one and only one unique outcome. It follows the law of conservation of energy perfectly. The problem? The huge problem? We can't prove that this beautiful, well-behaved solution will even exist when the flow gets really, really chaotic. It might just, poof, disappear. So, to get around that problem, Leray developed the weak solution, and this is a completely different beast. Instead of working at every single point in space and time, it only has to satisfy the equations on average, over a small region. And the huge advantage is that we know this solution exists for all time, no matter what. But, and this is a big but, it comes with some serious drawbacks. It might not be smooth, it doesn't have to perfectly conserve energy, and it might not be unique. So check this out. This table really lays out the dilemma perfectly. It's a classic engineering trade-off, right? Do you go with the perfect, ideal solution that might just vanish when things get tough? Or do you trust the rugged, persistent solution that might not give you a single, reliable answer? This exact trade-off has been at the very center of this problem for almost a century. And that brings us right to the heart of the paradox. If we have to rely on these weak solutions because they're the only ones we know for sure will stick around, what in the world happens if they aren't unique? This isn't just some abstract math puzzle. This is a huge deal. For anyone doing any kind of simulation, predictability is everything. You put in one set of inputs, you expect one set of outputs. If you can get multiple or maybe even infinite different outcomes from the exact same starting point, the whole predictive power of your model is thrown into question. I mean, determinism itself is on the line. And this graph, man, it just perfectly captures the nightmare scenario. You start here on the left with one single starting point. Maybe the flow follows this nice, clean, predictable black line. That's your strong solution, behaving perfectly. But what if you get the red line? What if it reaches a point where it can just split into multiple possible futures, the same exact past leading to different, equally valid tomorrows. For more than half a century, this was just a nagging suspicion. The brilliant mathematician Olga Ladezhenskaya famously conjectured that these non-unique solutions could exist, but nobody could prove it. It just stayed there, one of the most stubborn and important open questions in all of mathematics. So, how do you solve a 50-year-old math problem that has stumped some of the greatest minds in history? Well, it turns out not just with pen and paper, but with a powerful new team, human creativity, and machine precision. And then it happened. A landmark paper came out that claimed to have finally settled the debate. The authors delivered the very first rigorous proof that these Leray-Hoff weak solutions are in fact not unique. And the way they did it was by using a computer-assisted proof. Okay, so how did they do it? Their strategy was just brilliant. First, they mathematically constructed a very special, very finely balanced solution. The best analogy is to think of a pencil standing perfectly on its tip. Then, they analyzed its stability. They used a computer to search for a very specific way to nudge it, what they call an unstable eigenpair, that would guarantee it would fall over. And then, this is the absolute key, they used the computer not just to simulate, but to prove with total mathematical certainty that this instability exists. It used something called interval arithmetic to handle the massive calculations needed to put a hard boundary on all possible errors. It's something no human could ever do by hand, and it delivered a result with the same rigor as a traditional proof. That computer-certified unstable eigenpair, that was it. That was the smoking gun. It proved that if you have that pencil balanced on its tip, it doesn't just fall one way. It can fall in any direction. The system could spontaneously evolve along infinitely many different paths from one single starting point. The conjecture was no longer a conjecture. It was a proven theorem. So, the math is settled. A huge win for the mathematicians. But what does this actually mean for the rest of us? For the engineers, the physicists, the people trying to model the real world? For any engineer who's ever wrestled with a turbulence model like RANS or LES, this should sound eerily familiar. For decades, we've had to use statistical models for turbulence precisely because we can't predict the exact chaotic behavior. This result basically provides a fundamental mathematical reason for why that is. The unpredictability isn't just a practical limitation of our computers. It seems to be baked into the very equations themselves. But here's the thing. Maybe this isn't a flaw in the equations. Maybe, just maybe, the mathematics is telling us something incredibly deep about reality itself. Perhaps the equations are correctly capturing the fact that at the edge of chaos, where turbulence is born, physical reality itself loses its strict, predictable determinism. The math isn't broken, it's just reflecting a deeper, more chaotic truth about the universe. Now, let's be super clear. This proof isn't going to suddenly make your CFD simulations run perfectly or fix tomorrow's weather forecast, but it forces us to completely rethink our relationship with the equations we've trusted for centuries. It validates the gut feeling that turbulence isn't just a hard engineering problem, it's a fundamental mystery of mathematics and physics. And that leaves us with this really mind-bending idea. By proving that our very best model of fluid flow allows for one single past to split into an infinite number of futures, we haven't just solved a math problem. We've uncovered a deep and fascinating question about the nature of reality itself.